So what saponification value gives us an idea of is the RFM of the fatty acid chain. So my question was, what is constant for all fats? What is there in all fats? What is the base?
Glycerol.
Correct. Yes, glycerol. Somewhere close. Yeah, so you have your glycerol chain at the start of it. But what is it that then can change?
The fatty acid chain.
The fatty acid chains. I can have various fatty acid chains on it. So what the saponification value tells me is the RFM of those fatty acid chains. So whether they are a high RFM or a low RFM, and we'll get onto that in a wee second. Dinging. Okay, so. What we need to look at first of all is what actually is saponification. Saponification is really just a fancy word for the hydrolysis of our fats. Back down to, if we hydrolyze our fats, what are we going to get? What are we going to produce?
The glycerol and fatty acids.
Get the glycerol and the fatty acid chains. So really saponification is just a fancy word for the hydrolysis of esters. Can we remember last week we talked about fats being types of esters, particularly triglycerides or triesters, because there's 3 ester bonds. So what I'm doing is I'm just breaking those ester bonds, which we've done before, but particularly we're going to catalyze it using an alkali, particularly potassium hydroxide. Okay, so let's have a wee look at this. So we're going to do it for glyceryl tristearate. It doesn't specifically tell you in your specification that you need to know how to Can you remember when we're making a normal acid plus, don't write this down, when we're making a normal acid plus alcohol ester, what does the first part of the name come from?
The alcohol.
The alcohol. And what does it change its ending to? Oh, so let's say we had methanol, it would change to methyl. And then what does the acid change its ending to? O8. Well, it's oic acid and it changes to O8. So really just the IC changes to ATE. So let's say ethanoate. So what you've got in glyceryl tristearate here is you've got glyceryl instead of glycerol. Yeah? It's changed its ending to O. And then...
Glycerol and alcohol.
Pardon?
Glycerol and alcohol.
Yeah. It's a triol. There's 3 alcohol. So that came from glycerol, and then this one came from stearic acid. So can you see how I've changed my IC to ATE?
Yeah.
So that's how we name that. Is that alright? So oleic acid would form glyceryl oleate.
Yeah.
Yeah. So, yeah. Okay, cool. Right, so let's draw glyceryl tristearate. Actually, why don't you try drawing glyceryl tristearate? Draw your fat. Hopefully we can remember how to draw a fat. And they should have 3 stearic acid chains. No, just draw the molecule for now. I'm gonna have to... When I do hydrolysis, what is it that I actually do? Where do I break my molecule up? What does hydrolysis mean?
Addition of water.
No. Good, breaking up a molecule using water, okay, but it's not, you're not adding water to this molecule, you're breaking it up. So where do I break it? Break it. But whereabouts?
Between the C and the O.
Between the C and the O, good. So I'm going to break it here. So think about forming your esters. You've got acid plus alcohol. Now you're trying to do the reverse of it. What type of reaction is esterification? Begins with a C. Condensation. You're losing water. This is doing it the other way around. Okay. So I'm breaking. So this is obviously going to become my alcohol part, and this will become my acid part. Okay. So I'm going to take that off a wee second. Okay, so I'm going to write it as a reaction with potassium hydroxide. How many potassium hydroxides do you think I'm going to need? 3, because I've got 3 ester bonds to break. Okay. So,
That means 3 moles or what?
yeah. So for every 1 mole of glycerol tristearate I need 3 moles of potassium hydroxide. So what am I going to get back on this other side?
Glycerol.
Yep, glycerol
3 steric acid.
and 3 steric acids.
Shall I get 3 K of each as well? No.
Oh, good point. So it's not steric acids I get. No. Not quite steric acids, no. What happens when we use the alkaline hydrolysis? Good point.
Yeah, the K acids instead of NaOH.
Okay, so when we did it with sodium hydroxide, we got the sodium salt of our acid. So this is going to be the potassium salt of our acid. So I'm just going to write 3 because I can't be bothered to write it that many times. So it ends in CH3, and then I've got 16 CH2s, and then I've got COO. Okay, I think that's possible. That's an O as well that I've added in if you colour coded your potassium hydroxide. That's the O that's added in as well.
So Johnny add a couple of H's or something?
No, because if you think there's K, O, H, K, O, and H is what I've added on. No. So when it's alkaline catalyzed, you just write it as the reaction with the alkali itself. Pardon? Yeah, I have hydrolyzed it. But the alkali in reality is dissolved in water.
You can write it with water and the salt with water.
But the salt forms, so if you write it with water, then it's just a trickier job of actually balancing it. So when you do it with we did this with hydrolysis of esters. When you do it with the alkaline catalyzed, then you always form the salt of your acid, and that's what this cook thing is at the end. Is the potassium salt of my steric acid. Okay, so this is glycerol. And what do you think we call this other thing that we produced?
Where?
The potassium salt thing.
Potassium stearate?
Yeah. So what would the sodium salt of ethanoic acid be? Sodium ethanoate. So the same way as the potassium salt of steric acid is potassium stearate. Did we add any labels to the other side?
Nope.
Let's do that. So these potassium salts that we form, the potassium salts of the fatty acids, we call them soaps. And they are, funnily enough, used in soap. Is that right? Cool. So that's why this is called saponification, because we're forming soaps. But again, saponification is just a fancy word for the hydrolysis of our fats. Yes? Is that okay? Cool. Oh, sorry. Do you need this? Okay, so as I said earlier, saponification value gives us an idea of the RFM of the fatty acid chains, okay? Because the glycerol is always going to be constant, but it's the fatty acids that can change. So this is why when our iodine value, in our definition, we said the mass of iodine in grams. That's why you have to say in grams, because for saponification value, what do we notice?
Milligrams.
It's in milligrams. It's the mass of potassium hydroxide in milligrams. See, when you have to do your calculations at the end, you need to convert it into milligrams. Okay, so you need to remember that. And if you remember your definition, you'll remember that. You'll think, oh, the definition of saponification value is the mass of potassium hydroxide in milligrams. Required to completely hydrolyze 1 gram of a fat or oil. Okay. What we find with this is kind of counterintuitive. The lower the saponification value, the higher the RFM. Okay, I'm going to explain it a wee bit more in a second, but this is literally it. And you don't even need to know why this is, but because you will want to know why. And it's because if I have 1 mole of a fat, how many moles of my potassium hydroxide am I going to need? Yeah, you're right, 3 moles of the alkali. So it doesn't matter what size my fatty acid chains, I'm always going to need 3 moles of alkali for every 1 mole of fat. Okay, say I have 1 gram, your definition is about 1 gram of your fat. Say I have one that has a really short chain. So this one is going to be our short chain. I don't really know where I'm going with this, but. And this one is a long chain fatty acid. Okay, I have 1 gram of each. Which one am I going to have more molecules of?
The short chain.
The short chain. Why?
Because there's less atoms in the same molecule, but there's the same amount of mass in each.
Less atoms. Say that again?
There's like less atoms in each molecule, but there's the same amount of like mass. So say 1 gram of each, there's have to be more.
Yeah.
Molecules.
Okay, so say for example, this had an RFM of, well, let's not do that. Let's say like 0.1 grams per mole. Yeah, that would be our unit of RFM if we use them, molar mass, grams per mole. Okay, so it's saying that 1 mole of sodium is 23 grams because the RFM of sodium is 23. So say the RFM of that, the short chain one is 0.1 grams per mole and the RFM of the long chain one is 0.2 grams per mole. How many short chain fats am I going to have in a mole? 10. How many long chain ones am I going to have?
5.
Just 5. Can we see why that is?
Wait, what was your question?
How many are in a mole? Okay, so with my short chain ones, because I have more molecules in a mole, and for every molecule, I need how many potassium hydroxides? 3. Okay, so how many potassium hydroxides am I going to need for my short chain one? No, 30. And how many am I going to need for my short chain, long chain one? No, sorry. How many am I going to need for my long chain one? 15. I'm going to need 15 moles of potassium hydroxide. If I convert that into the mass of potassium hydroxide, which is going to need a bigger mass of potassium hydroxide? The one on the left. Okay, so I would times each of those by the RFM, which is 56. Don't know what that gives me, but obviously this one's going to be much bigger. So a higher saponification value means a shorter chain fatty acid, a lower RFM. Okay, again, you don't really need to know that, it's confusing, but yes, let's proceed. Right, so, and this will kind of introduce us to the calculations. So if we have our fat plus 3 moles of potassium hydroxide is going to give us glycerol plus our 3 soaps, we'll call them. Okay. How do I work out the mass of my fat? Or sorry, the number of moles of my fat? Okay, so we said it's for 1 gram divided by the RFM of your fat. I don't know what the RFM of my fat is. Okay, if I want to work out how many moles of potassium hydroxide reacts with that, how do I work that out? Yeah, the ratio is 1 to 3. And so my number of moles of potassium hydroxide is going to be 1 gram of my fat divided by the RFM of the fat times by 3. Yes? With me? Okay, so then the final calculation will be convert that into the mass of potassium hydroxide. What's the formula for working out mass? N times RFM. So my number of moles is this. So it's 1 gram of my fat divided by the RFM of the fat, times by 3, times by the RFM of potassium hydroxide, which is 56. Okay. What is the only thing that is affecting this value of mass? The RFM, because 1 is always going to be the same, 3 is always going to be the same, 56, they are constant numbers. The only thing that can change is the RFM. If that is a bigger number, what effect will it have on the mass? It'll be lower. If it's a smaller value, it'll be higher, because it's on the bottom half of the equation. So 1/2 is bigger than 1/4. Yeah? Okay, again, you don't need to worry about that too much. And which is basically what I've just done on the previous page. So, for example, number of moles is mass over RFM. If we have 1 gram over RFM of 100, what would our number of moles be? No, that's not right. 0.01. Okay, and then if I had a different one which had an RFM of 200, what would it be?
Is that 1 over 100?
Ah, it is. It doesn't really look like it, does it? 0.005 moles. So mean. Right, so you can write that in if you want, just to show you that the larger the RFM, the smaller the number of moles. So the smaller the number of moles of potassium hydroxide, so the smaller the mass of potassium hydroxide, so the smaller the saponification value. Cool. Right, so we're going to do, this is generally not how this would be asked. It would be asked as a whole kind of titration calculation, which is a little bit crazy, but that's okay. And we'll do that in a second.
Is this stuff on our test?
Yeah.
Is it actually?
Yeah.
I didn't know.
To the end of this topic. Okay, so this wouldn't generally be how this is asked, but we can work out, if we know what our fat is, we can work out the theoretical saponification value. So we're going to do it for glycerol tristearate. What I want you to do is work out the RFM of glycerol tristearate. General equation for saponification values is that you've got your fat plus how many moles of potassium hydroxide? 3. Gives me what on the other side? Glycerol plus how many potassium salts? 3. And I'm just going to write soaps.
It shows how like cavemen make soaps from one of the questions. It's like cavemen do this.
No way. I don't know. Cavemen did this. No one will actually say.
Okay, so you can, if you want, write your whole equation out for what glycerol tristearate is and all that, but generally the equation's always going to be the same. Always 1 mole of your fat plus 3 moles of your potassium hydroxide. Alright, so to do this is then, from this point, it's a simple moles calculation where I do N equals mass over RFM. What's my mass?
There's no way they knew what they were doing.
1, because it's the mass of potassium hydroxide for 1 gram of fat or oil. What's my RFM? 890. That works out as 1.12 times 10 to the minus 3 moles. How do I work out then how many moles of potassium hydroxide would react with that? Why is that?
3 moles.
A ratio.
Of 1 to 3 ratio. Okay, so times that by 3, you should get 3.37 times 10 to the minus 3 if you keep it accurate. Then how do I work out the mass of potassium hydroxide used? Mass equals N times RFM, which is 3.37 times 10 to the minus 3 times by 56, which should give you 0.189 grams. Is it cool? Yet?
I know, I mean, that's not
Brilliant! One person on the ball. This is not my saponification value because
You didn't ask if it was, you just asked what it was like.
I asked you was it cool, you said it was cool, and I asked you was it cool. It's not cool yet. Times it by 1,000, why? Needs to be in milligrams, so that gives us 189 milligrams. So your saponification, your theoretical saponification value for glycerol tristearate is 189 milligrams.
Wow.
That means it would take 189 milligrams of potassium hydroxide to hydrolyse 1 gram of glycerol tristearate.
That was fun, man.
In reality, you'll get this as a back titration question, which is a little bit more difficult. And this is kind of your experimental method. The experimental method doesn't actually say in your specification that you need to know how to do this, but you kind of need to know how to do it in order to make sense of the calculation. So, read this with me a second. All right, you've got your fat, and you then add your potassium hydroxide to it. So just think of our equation here: fat plus 3 KOH goes to whatever. Don't need the other side of the equation. All right, so you get your about 1 gram of your fat. What does it mean? Weigh accurately about. Weigh out accurately about 1 gram of fat.
It's like to an appropriate degree of accuracy.
Plus or minus 1 degree, or 1 gram.
Not quite. Yes, like, yeah, around about 1 gram, but what does it mean to weigh out accurately about 1?
It has to be kind of close to
It's
one.
like close enough, but it doesn't have to be exact.
No.
Analysis.
I can't remember.
Can you remember this from last year?
We didn't do this last
You
year.
did.
We did this last year.
In your practical.
Yeah, we did this last year. I would swear.
Because what we would have done, we would have actually written it accurately, approximately 1 gram.
Approximately 1 gram.
But what does that word accurately mean?
Close to one. Do it well, but like.
Because you can't know the like if it's like exact value because you can only measure in certain like decimal places.
Do it with a good scale.
No.
Like if your scale does the 2 decimal places, you can't get it to 3 decimal places.
Yeah, but no.
We just tell us
Yeah,
what
but-
about it.
So it means you need it around about 1 gram, so 1.02, 1.05, whatever, but I need to know exactly how much I've weighed out. So it just means record what you've weighed out. Does that make sense?
Yeah.
So it's around about 1 grams, but as long as I know exactly how much I have, not to the however many decimal places my balance allows me. Yes? But you need to know how much, otherwise I can't do my calculation if I don't know exactly how much fat I have. Yeah? Okay, cool. Glad we remember that. Then you add your potassium hydroxide. Tends to be 50 centimeters cubed of this concentration, which is 0.1 potassium hydroxide. In ethanol, it says there as a common solvent. What do I mean by a common solvent?
It's dissolving it, doesn't it?
What does? What does it mean, common solvent?
It's common. You find that in most places.
No.
It's
Good
the
answer,
same
but
state as the
no, that would be a heterogeneous or a homogeneous.
same polarity or something.
No, common solvent. What I needed to be a common solvent too. This is good practical chemistry we've got here.
saying that some solvents are lesser than other solvents?
No, no.
Just tell us what's the case, please.
It means that it dissolves both. A common solvent means that it dissolves both. What do I need it to dissolve?
Fats and the other thing.
Which is what?
Alcohol.
Soup. Yeah, we get to
Potassium hydroxide.
I said that, so I should not. Oh, I said carry it, I should.
Okay, maybe we might need to make a note of that, that's what a common solvent means, is that it dissolves both things that are in the reaction here. Because if I add in some water, it'll dissolve the potassium hydroxide, but what will it not dissolve? The fat. Okay, so my potassium hydroxide and my fat can't react together because they're not in a common solvent. Is that okay?
Yeah.
Great.
Oh, a common solvent is in both CR. I never saw that. You must have worded it wrong or something.
It actually makes sense, it makes so much sense, I don't know why.
Yeah. You're not like found in nature, that's weird.
No. Okay, then you reflux it. So
Have you eaten all that?
No, it's no good. I'm not, I was just sitting on my desk.
you reflux it to get the potassium hydroxide and the fat to react together. Alright? In a common solvent of ethanol, so they actually react together. Okay? So you reflux it for about 45 minutes or until the solution is clear. And when the solution is clear, it tells you that saponification is complete, because both glycerol and your potassium salt of your acids will dissolve in water. So that's why your solution becomes clear at the end of it. Does that make sense? That means saponification is complete because you have no more fat anymore. Okay. So what we'll do is just a bit like last week when we were adding our iodine in excess, or our ICL in excess, or whatever we added in excess. The 50 centimetres cubed. 50 centimetres cubed of my potassium hydroxide is in excess as well. So some of it will hydrolyse the fat, but once it's hydrolysed all the fat, there'll be a little bit of it left over. How could I find out how much potassium hydroxide is left over?
You can have to know double formula equation use.
Yes, back titration in other words. So what could I titrate potassium hydroxide, excess potassium hydroxide against? Get indicator. Potassium hydroxide against sodium hydroxide. Hydrochloric acid or sulfuric acid or whatever type of acid you like. Hydrochloric acid is the easiest because you get a 1-to-1 ratio. Okay, so that solution I'm titrating against hydrochloric acid. That tells me how much potassium hydroxide didn't react with my fat, and then I do a back titration calculation to work out how much did react by doing initial minus what didn't react. Yeah? Okay? Right, let's do an example. Okay, it will not be written as simply as this in your exam, but this is just me simplifying it down for the first example of my calculation. So, I can't remember how we set these out last year, so tough, yeah. So, we've got our general equation, fat plus 3 potassium hydroxides gives me glycerol plus 3 soaps. Or 3 soap, whatever. Okay, what is my second equation then? My excess potassium hydroxide is reacting with, yeah, HCl. What is that going to give me?
Ooh, KCl and H2.
Good. KCl plus H2. What type of reaction is that? Neutralization. Great. Okay, so the information that I have is that I need 22 centimetres cubed of my hydrochloric acid to neutralise the excess potassium hydroxide. Is that okay? So, the place that I start is right here then. Okay, how to work out the number of moles? Not quite. Not 1-to-1.
What? Well, you need to find out what's reacting.
CV, good. Concentration times 1.
Just 0.1.
Okay. That is concentration though.
Yeah.
You do know that, yeah? Okay.
Times that by, well, 50 over 1,000. That's what you want to do.
Yeah, 50,000. I'll give you.
I don't really want to do 50 over 1,000
Why not? 50 times 10
because that's not how many moles of, or the volume of hydrochloric acid that I've used. No, but how much hydrochloric acid have I used?
Never mind, Mom.
I'm going to convert it to decimeters cubed first. 0.00
Yeah.
2. No, that's not right. 0.22. 0.022.
Is that
Which,
not the volume of KOH?
no, volume of hydrochloric acid required to neutralise excess KOH equals 22 centimetres cubed. Yeah?
KOH equals, make it look like that, isn't it?
Yeah, but you haven't read the whole sentence.
Yeah.
Okay, so that gives us 0.0022 moles of hydrochloric acid was used to neutralise the excess KOH. How do I work out how much excess KOH there was?
Bring it up in the class. I'll take that seat.
Good, ratio is 1-to-1, so 0.022 moles. And that is the excess. Okay. I need to work out first of all the initial moles of potassium hydroxide that I added.
Yeah.
So initial KOH. So I'm going to use my equation N equals CV. Again, what's my concentration of potassium hydroxide? 0.1. What's the volume of potassium hydroxide that I initially added? 0.05, because it's 50 centimeters cubed that I added, and that gives me 0.005 moles. Okay, so how do I work out how much KOH was used? Yeah. So the KOH used is 0.005. That's how much I started with, and I worked out that there was 0.0022 moles of excess, and that gives me 0.0028 moles. Are we okay to this point?
Yeah.
Okay, I'm just going to bring this up here. This is how many moles of my KOH was used in my top equation to react with the fat. So 0.0028 moles. I don't need to work out, don't need to bring that across to my fat, because what I'm interested in working out is the number of moles of potassium hydroxide. No, because it's a separate equation. It's when you're going.
And that's the reacting moles, yeah.
It's when you're going within the same equation that you need to do your ratios, but not because what I'm saying in the first equation is that well, if you think about it the other way around, the excess moles, I'm saying that I have 0.0022 moles of excess. If I was then to divide that by 3 going to here, I'd be saying it's suddenly saying that I have 0.009 or something, which I don't, because I have 0.0022. So when you're going between two different equations, you don't include the ratio. Okay. So how do I work out the mass of potassium hydroxide that I've used? Mass equals N times RFM, which is 0.0028 times 56. Probably this number 56 will be in your head, hopefully. That's the RFM of potassium hydroxide. That works out as 0.1568 grams. But
Times by 1,000.
times it by 1,000 to get it into milligrams. Sorry, I've run out of room. It's 156.8 milligrams. And that is your saponification value. Oh, not yet. Not yet. Why not yet?
It gives you the mass of the fat.
Because it gives you the mass of the fat. So this is for 1.053 grams of fat. What is my definition of saponification value? Tell me. It needs to be for 1 gram. So I need to do for 1 gram of fat. It's going to be 0.8, sorry, divided by 1.053 times by 1, or essentially just divide by your mass of fat, and that works out as 148.9. If you want to make a wee note, it doesn't make any difference to your calculation, but if you were to be finding it for 2 grams of fat, you need to divide by how much you have and times by how much you wanted to go to. And that is your mass of fat given in the question. So your final step is just working it out for 1 gram of fat. Oh, what are my units? Milligrams. Yes?
Yeah, no.
Okay, so same idea. We're reacting our fat with excess potassium hydroxide, then we're titrating the potassium hydroxide against hydrochloric acid to work out how much excess that there was, how much that was used by the fat, and so I can work out the saponification value. Okay, so what does this word mean? Ethanolic solution. Ethanolic solution. Ethanolic solution. Yeah, dissolved in. Okay, but that doesn't really matter. Okay, so first reaction that we've got happening is the fat plus the 3 potassium hydroxides. Gonna need to keep up. Gives us glycerol plus our 3. So, okay, then what's our second reaction?
KOH plus HCl gives HCl plus CO2.
Okay, so the question tells me that the solution required, so I'm almost going to the end of the question to get what I need for my first part of the calculation. It tells me that the solution required this much hydrochloric acid. I need to work out how many moles I have of this. Do that by doing N equals CV. My concentration of hydrochloric acid is 0.1. The volume is 12.5 centimeters cubed. So that is 0.0125. That gives me a number of moles, 0.00125 moles. Okay, to work out how many moles of potassium hydroxide I had in excess, I do my 1-to-1 ratio, which is 0.00125 moles. Okay, now I want to work out, that's the excess potassium hydroxide. I want to work out how many moles were used by my fat in the first place. So initial KOH, we're going to do N equals CV. What's the concentration of the potassium hydroxide initially added? 0.125. What's my volume? How much of it did I have? 25 centimeters cubed. Okay.
It's on the spread there.
It's the concentration 0.125, yeah. Times 0.025. 0.003125 moles. So that's how much I initially added. This is the excess. So how do I work out how much did react with my fat? Take them away. So KOH used is your 0.003125. Take away the 0.00125, which we worked out was the excess. That should be 0.001875 moles. So that is how much did react with my fat. Okay, so I can bring that up to this equation. Don't really need this part of the equation that much, but bring that up here. .001875 moles of my potassium hydroxide. What do I need to do now? No. Because I'm working. No.
Times it by 56.
Why? Good. I want to work out the mass of my potassium hydroxide. So I do my moles times by the RFM, which is 56. That works out as 0.105 grams. What do I need to do? Times it by 1,000 to get it into the milligrams of potassium hydroxide. Okay, that is for what mass of my fat? 0.84 grams of fat. what do I need it in? 1 gram of fat. So for 1 gram of fat, it is going to be, how do I work that out? Yeah, it's going to be 105 milligrams divided by my 0.84 grams. That's just coming from the fat, the mass of fat given to me in the question. You can times it by 1 if you want. That's because you want it in 1 gram of fat. That works out as 125 milligrams. So that means that 125 milligrams of potassium hydroxide is required to hydrolyse 0.84 grams of this fat.